Today we're going to be talking about angles in polygons. And first we need to define what a polygon is. So what's the difference between the figures on the top and the figures on the bottom? Figures on the left, figures on the right. Well, notice this first one. You have all pieces, all segments connect, and nothing dents in. Like for example here, if I were to pick 2 points and I draw a line, part of that line is going to be outside. This part is curved. This one, you have one vertice, another vertice there, another vertice there. They kind of intersect, part goes in. The top are going to be polygons. The top ones are polygons. Okay, and a polygon is connected, segments connected by vertices where no two segments intersect. So for example here, these two segments intersect, so this is not a polygon. This has a curved line to it, so it's not a polygon. Now there's a difference between the top two polygons. The top one, this first one is convex. A convex polygon. Versus a concave or a non-convex polygon. I think about it as concave because it caves in. When I have a segment where two lines that are inside the polygon, if I draw a segment between those 2 points, part of that segment is going to lie outside. So we have a convex versus a non-convex. All the time, most of the time, I would say 99% of the time, we're going to be dealing with convex polygons. Okay, a diagonal is a segment that joins two non-consecutive vertices. So for example, in our pentagon down here, that would be considered a vertice. Or I'm sorry, a diagonal. That would be considered a diagonal. Okay, two non-consecutive vertices. Because if you're joining consecutive vertices, that's going to be a side of our polygon. Now a regular polygon, make sure you know this definition. A regular polygon is going to be a polygon that is equilateral, so all sides are equal, and equiangular. All the angles are equal. Okay, so keep that in mind. Now these angles that I've arced in blue, that angle is an interior angle. This is an interior angle. If we were to take one side of our polygon and extend it, this angle here would be an exterior angle. Versus inside here, that was an interior angle. Okay. Now this is usually something that I like to derive with the students in class. Since we're doing this as a video, we're going to derive it in the video. And we're going to be looking at patterns. So the number of sides, if I have 3 sides of a polygon, and yes, I want this chart in your notes. If I have 3 sides of a polygon, its special name is triangle. Number of diagonals, so I have a triangle over here. I can't draw any diagonals, so this is 0 diagonals. The sum of the interior angles, well, all of the angles in a triangle add up to 180. Now, a quadrilateral. Number of diagonals. Here's a quadrilateral. I have 1, 2 diagonals. So I have 2 diagonals. Sum of the interior angles. How we get that, or how I like to explain that to students, is if you just draw one diagonal. You've split this into 2 different triangles. So I have 1, 2 triangles. Those 2 triangles are going to equal all the angles in those triangles are going to add up to all of the sums of all the interior angles. So that's going to be 360. Okay, next, with a pentagon. Number of diagonals. So this vertice here is paired with 1, 2 other vertices for a diagonal. Then I have this one up here is paired with 3, 4. Then I have this one here is paired with this one. Well, that one's already taken care of. Or this one down here, so that's 5. Now let's look down here at this next one. Well, this diagonal, I have duplicates. This next one is again another set of duplicates. So for our pentagon, we only have 5 diagonals. Now this is sum of the interior angles. So let's just look from one vertex. That's what's a little confusing. From one vertex, let's draw all of our possible diagonals. How many triangles do I have? I have 1, 2, 3 triangles. 3 triangles. All of the angles in our triangle are going to end up adding up 180 times the number of triangles. Well, that's going to be 540. Next, our hexagon. Let's see if we can maybe start coming to some conclusion. So this hexagon, this vertex here is paired with, a hexagon has 6 sides, so 6 vertices is paired with 1, 2, 3. So I had 1 vertex is paired with 3. 4, 5, 6. This vertex here is paired with 1. So that's our 7th, our 8th, and then this vertex is paired with, so that's our 9th one. So notice how each vertex is paired with 1, 2, 3. 3 less than the number of vertices. So the number of diagonals in our hexagon is 9. And now let's look at the sum of the interior angles. Okay, so let's look at this. When I draw in our triangles, so I have drawn segments, I have 1, 2, 3, 4 triangles. 4 times 180 is equal to 720. Now let's look at what 7 septagon is. That's a special name. 8 is an octagon. 10 is a decagon. But let's try and come up with some sort of pattern for the sum of the interior angles. So let's say of our septagon, which I have one drawn over here. Notice how the number of sides n, and that's just going to be an n-gon. So like for 15, we're going to have a 15-gon. But let's talk about if I had 7. Let's talk about how many triangles I get. 1, 2, 3, 4. 1, 2, 3, 4. I have 5 triangles. So how does the number of sides compare with the number of triangles we get? Well, here 4 I had 2 triangles. When I had 5 sides, I had 3. 6 sides, I had 4. 7 sides, I have 5. 8 sides, I wonder if I'm going to have 2 less, because it looks like 2 less is my pattern. So let's test that out. So here's my octagon. 1, 2. This is just figuring out for some of our interior angles. I have 1, 2, 3, 4, 5, 6. So it's 180. Our pattern is 180 times the number of sides minus 2. 180 times the number of sides minus 2. 180 times the number of sides minus 2. So our pattern, 180, or our formula I should say, is 180 times n minus 2. Now let's look at our diagonals, and the diagonal one is a little bit more complicated. Let's look at our diagonals of our pentagon here. So the diagonals of the pentagon. Okay, so diagonals of the pentagon. For pentagon, I have this vertex. Each one of these vertices is going to have a certain amount of diagonals coming out of it. How many diagonals can I draw? I can only draw to 1, 2 other points. I can't draw to that vertex, and obviously I can't draw it to its original. So for an n-gon, it's the number of vertices times by the number of diagonals I can draw out of that vertex. Well, that's n minus 3. Now I have to divide by something, because if I go down to this vertex, that diagonal is the same one that I've already drawn, so I have to divide by 2. Okay, so that's a lot of formulas. Let's go through those formulas. Please make sure you have these names in your notes, okay, because they're going to disappear here in a minute once I click on them. So the sum of the angles of a polygon is going to be 180 times n minus 2, where n is the number of sides, not hashtag sides. It's the number of sides. Now the sum of the exterior angles. Make sure you know what this formula is. Sum of the exterior angles is always going to be 360 degrees. Because think about it, as you get closer and closer and closer to drawing, like say you want to draw 487 sided polygon, well that's going to look a lot like a circle, so it's 360. Number of diagonals of a polygon. The number of sides times n minus 3. Why is it minus 3? Because each diagonal can only be can't be paired with the 2 vertices on either side or itself, and it's cut in half because sometimes you'll trace a diagonal twice. Now this formula, measure of each interior angle of a regular polygon. You find out the sum and then you divide by the number of sides. Okay, so let's go through some examples and see how we're going to use these formulas. Okay, first example. Find the sum of the measures of the interior angles. Also find the number of diagonals of a septagon. Now a septagon, you need to know what that word means. That means a 7-sided figure. And that's why I needed you guys to write down that chart. So n equals 7. So our interior, the sum of the interior is going to be 180 times 7 minus 2. And that ends up being 900. The sum of the exterior. The sum of the exterior angles is always 360 degrees. So that never is going to change. The number of diagonals. Okay, remember that formula. Number of sides times number of sides minus 3 all over 2. So I have 7 times 4 over 2. 2 and 4 can cancel to be 7 times 2, which is 14. 14 diagonals. So it's just using the formulas. Find the measure of the interior and exterior angle of n interior, so that means 1 interior and exterior of a regular 15-gon. So what I do, the interior, what you do is you take number 180 times the number of sides minus 2, divide that by the number of sides, because each interior angle is going to be split up. Since they're all equal, they're split up equally between the 15 sides. So this is 156 degrees. Our exterior. Again, there's really two ways to do it. Because when you have two sides that meet of a polygon. Now, I don't know what a 15-sided polygon looks like, but this would be our interior angle. We know the exterior angle, if I just extend this line, is a linear pair with my interior angle. So I could do 180 minus 156 to get me 24. Also, what are you doing? You're taking 360 degrees, because that's what they all sum up to. Divide by the number of sides we have, or number of vertices, you also get 24. So two different ways of thinking about it. Next example, a polygon has 54 diagonals. How many sides does the figure have? So 54 equals our formula for the number of diagonals. N times n minus 3 all over 2. Now, get rid of that 2. Multiply both sides by 2. So I get 108 equals, those 2's have canceled, so that goes away. Distribute the n through. Bring the 108 over to the other side. Now I need two things that multiply to be 108, because we solve a quadratic by factoring. Two things that multiply to be 108, but we're going to add to be a negative 3. Those end up being n minus (12) and n plus 9. Then you set each one of those factors equal to 0. So n can be equal to 12 or negative 9. Can I have negative? What am I trying to find? I'm trying to find the number of sides. I can't have a negative number of sides. So we have 12 sides. Now think back. This should work. So if you plug in 12 to this formula, to the blue piece, you should get 54 out. And you do. Okay, next example. The angles of a hexagon, a six-sided figure, are consecutive odd integers. What is the degree measure of the largest one? So the first one is x. Second one is x. Now it's odd. So I have to add 2, because if I added 1, I would get an even number. Now I take my original, I add 4 to it, because I want the next odd integer. And I keep going until I have 6 things. This is 1, 2, 3, 4, 5 sides, and now our last one, 6 sides. So x is our smallest angle measure, and I keep adding, even though it says odd integers. I was thinking about this as I was writing it out. You guys might be confused because I have even numbers written there. What that means, that just means that I keep adding a number to x to make it odd. I've designated x to be odd, so when I add 2 to it, I'm going to get another odd number. Okay, now the sum of a hexagon is 180 times 6 minus 2. So I have 6x plus 30 is equal to 720. 6x equals 690. X is going to be equal to 115. So this is our smallest angle. To get the largest one, x plus 10, that was our largest angle. So I add 10 to it, x is going to be equal to 125. Or not x, the largest angle. Okay, next example. BC is one side of a regular n-gon. The sides next to BC are extended to meet at W. Find the measure of angle W, that means angle W, in terms of n. So BC. And then I don't know how many sides it is. So these sides are extended so that they meet at a point W. I need to find the measure of W in terms of n. So this is a regular n-gon. So what is each one of those exterior angles going to be? Each one of those exterior angles is 360 divided by the number of sides. Now, I have two of those. Those are both equal. Plus, angle W is going to equal 180. So what do I have? I have 720 over n, because I multiplied 2 times 360, plus angle W equals 180. So angle W is equal to 180 minus 720 over n. I need to multiply the 180 by an n over an n so that I can combine like terms. Angle W thus is equal to 180 n minus 720 all over n. If you factor out 180, that's what you get. Okay, you have 5 lesson questions for today. Please make sure that these are submitted on time.